Here we are, my friend. Today we start our course in the C programming language. The course is based on the amazing book written by Carnegie and Ritchie, which is this one. As you can see here, this is the gospel of the C programming language and probably the gospel of computer science in general, because there is a lot of stuff inside this book that you need to understand in order to become a programmer, software engineer. So we are gonna disassemble, we are gonna decipher this book step by step in a very, very digestible way. My goal is to propose to you all the ideas inside this book in a super easy, comprehensible way. If you don't understand what I'm saying, that's my fault, not your fault. Because this book is not very easy if you start from zero, like I was. Initially, I didn't understand anything about this book when I was starting to learn programming. And I just want to give you a roadmap. Basically, you can read the book with me. And essentially, that's what we're going to do. We're going to read the book together. These videos are going to be highly practical in the sense that we're going to spend a lot of time coding. It is not just going to be a spoon-fed type of video. This doesn't work. This doesn't get any good results. This is just a tutorial L in which you have to escape as soon as possible. We're going to read the book, understand the principles, and then we're going to learn by doing. It will be a sort of tutoring. We are reading the book together. I'm going to do the exercises. And you will see how I move into the terminal, how I create programs, how I launch them. So basically, you're going to see all the deal of computer science, of programming with me, just watching what I'm doing. And by osmosis, by understanding a lot of comprehensible input, that's what I'm trying to do to you. I'm just trying to do as much as possible comprehensible input, stuff that you can understand and immediately apply and immediately test by yourself. You will absorb all this knowledge, so you just have to relax, watch what I'm doing, and you will learn hopefully a lot of stuff. So find yourself a copy of the book. I guess it's not gonna be terribly difficult to find online, right? And yeah, we are ready to start. We're gonna start from chapter 2, because the first chapter is just a basic overview of all the big ideas, but you need to be a programmer to understand chapter 1. As strange as it sounds. I will use a lot the terminal, of course, and Vim, which is the tool in which we write code, in which we write stuff. I already made 2 videos in which I explained the ideas behind the terminal and behind Vim. So if you don't know what I'm saying, if Vim and the terminal sound very strange to you, well, you can check my videos so you can basically follow me in these lessons. All right, that's it for this intro. We are ready to start. So chapter 2 is all about types, operators, and expressions, basically the building blocks of your code. I think you already know what data types are. I already explained in my fundamentals videos, but today we're going to go a little deeper. We are going to understand a little deeper this concept of data type and the concept of a size of a data type, namely, which is the limits of a specific data type. What does it mean to have a limit? So just a quick recap to be everybody on the same page. We have our marvelous computer, which is, at the end of the day, a calculator, an arithmetic logic calculator, and a RAM. So you have some numbers inside the RAM that are processed by the ALU, the calculator, which is inside the central processing unit. The RAM is the place where you stock numbers in a binary form, and this is the real chip. This is the real deal. You see inside your computer this green motherboard, in which find this 4 GB, for example, RAM, which is a simple chip. We programmers perceive the RAM as a series of bytes. A byte is an 8-bit object, means that you have a line with 8 light bulbs, 8 transistors that can be turned on and off. Basically, a RAM is this object here. Turning on and off these light bulbs, we can abstract numbers, right, in their binary form. So a byte, as I told you, is just a line with 8 light bulbs that are just transistors. You already know this stuff, so we can go on. So inside these bytes, we can store stuff. We can store data types. We already know that we have 2 kinds of data type. We have integer types and we have float, real types. Namely, we have numbers, integers. Integer simply means from Latin something that is not broken, intero in Italian, while real type means a number that has a point, for example, pi 3.14. This is a real number. We have 2 families of data type. Inside the 2 families, we have different sizes. For example, we have a char, a short, an int, and a long for the integer type, and float and double for the real type. I already explained to you that there is a real core difference between the way data is stocked, if it is in the integer type or if it is in the real type. So I prompt you to watch my previous video if you think this is kind of odd or this is kind of not really well understood. So if you read from the book in chapter 2 in data types and sizes, you read, there are only a few basic data types in C. You have char, int, float, and double. As you can see, there are not short and long. What is that? What does it mean? Well, you now know that I haven't told you the full story, because short and long are not really a basic data type. They are indeed qualifiers. They are not a data type. As we can read from the book. In addition, there are a number of qualifiers that can be applied to these basic types. Short and long apply to integers. These are qualifiers that apply to the integer data type. So short and long are not basic data types like char and int. They are qualifiers, but when we say short, it's obvious that we imply an integer data type, because we can only apply these qualifiers with integer data types. When we say long, we of course imply a long integer. So here we have short int sh. This is an integer short, and a long int counter. This is a long integer. Well, in the real world, in the real code, we just omit the int. We say short or long. We imply that, of course, this is an integer. We cannot use qualifiers such as short along with floats, with real numbers. So in every practical sense, short and long are like basic data types, such as char and int, right? You can just perceive short and long like two basic data types, even though you now know that these are just qualifiers. You will never find in codes like short int sh or long int counter. You just find short and long, okay? These qualifiers are pretty useful because they give you a surgical power on how to use your memory, right? If you say, I want an integer, but I don't want to occupy too much memory for performance-wise reasons. Well, only 2 bytes. I don't need a big number, so just give me 2 bytes in memory. You can say short and you get 2 bytes. You don't waste or bytes, for example. If you need a very big number, you can say, I want a long number, and you have this qualifier. So basically, these qualifiers are just tool to very surgically take as much memory as you need. This is very powerful performance-wise, because C really allows you to control very well the memory. Of course, nowadays, with very big memories, this doesn't make a lot of sense, but imagine back in the days when memory was very expensive, how useful it was to have such a fine control of resources. So, long story short, we have integers that can be 1 byte, 2 bytes, 4 bytes, or 8 bytes, okay? Even a char is just, at the end of the day, 1 byte integer, and you will see when we're going to talk about the ASCII code. We call it char, 1 byte, because that's what we use for storing 1 letter, because we don't need a big data type. So we have an integer of 1 byte that we call char. This is an abstraction, of course. We can say 1 byte, 2 bytes, 4 bytes, 8 bytes in the integer form. Stock number in an integer way. Cool. Now, these data types are not always 1, 2, 4, and 8 bytes. For example, let me explain. As we can read from the book, the size of a data type is hardware dependent. What does it mean? Well, depending on the machine, the size can change. 99% an integer is going to be always 4 bytes, but it's compiler dependent. The compiler is just a program that allows you to translate source code program into an executable, for example, your hello world program, into the actual executable code that your computer can execute. There can be cases where an integer can be, 2 bytes, or a long can be 4 bytes. It is compiler dependent. I repeat to you, we can be almost sure that this is what is going to happen inside your computer. If you have a Mac, for example, you're going to have a char of 1 byte, a short of 2 bytes, an integer of 4 bytes, etc. We have a very cool operator, which is called the sizeof operator. You will see at the code that at the end of this video, we're going to do together. Basically, this sizeof operator is telling you how much space this data type is taking inside my machine. Okay? So we can always know what is the size of the object inside every machine, so we can make programs that can run everywhere. The only thing, as you can read, that we are guaranteed is that short is no bigger than int, and int is no bigger than long. But maybe int and long are equal. We don't know. Its implementation is compiler, is hardware dependent. We don't know that. But we have this progressive way of seeing the data types. We don't have a long that is smaller than an integer, okay? This is guaranteed. Now, let's move on. Let's watch other 2 qualifiers. Now we have the signed or unsigned qualifiers. What does it mean? Well, you know very well that numbers are both positive and negative, right? So we can even very surgically discipline if the number has to be negative or only positive? With the signed or signed qualifier, I think it's fairly simple, right? You know that in a choose complement machine, if you don't understand this concept of choose complement, I made a video, so I prompt you to watch. We have the first bit that is always referring to the sign of the data type, right? For example, here we have 1 byte, so we are dealing with one char. The first bit is telling, hey, this number is negative or this number is positive. We have 1 bit that is delegated to discipline the sign of the number, while we have the rest of the bits which discipline the actual value of the byte. Okay, so what is the implication of this line of reasoning? Well, that's we have 7 bits for the value, the actual value, right? If 1 byte is delegated for the sign, for telling me, hey, this is positive or this is negative, it means that we only have 7 bits for the actual value. Okay, so how much value can I stock inside 7 bits? Well, you know that we can stock a value which is 2 to the power of 7. Why 2 to the power of 7? Well, because this is a binary object, right? If you struggle to understand this point, let me explain better. Let's pretend we are dealing with decimal numbers, and we have 2 figures, 2 digits that we can use to stock a certain value. How much value can I stock inside 2 digits? I can stock 100, right? I can stock from 0 to 99. What is 100? Well, this is 10 per 10, right? 10 per 10. What if I have 3 digits? Well, I can stock 1000 elements, right? Because I have from 0 to 999, 1000 patterns. And this 1000, where does it come from? Well, it comes from 10 per 10, 100 per 10. Basically, you have an exponential growth. This is the combinations that you can have with the way in which we encode numbers, right? With the way in which we encode value. That's the same line of reasoning here. If we have 7 bits, we can have 2 to the 7. It's multiplying 2 per 7 times. It's like before, it's like multiplying 10 per 3 times. We have 3 digits. Here we have 7 digits, but we are in a binary base value, so we do 2 to the 7. 2 to the 7 is 128 possible patterns. So for positives, we can encode from 0 to 127. And we have negatives that range from minus 128 to minus 1. Of course, we have minus 128 because we don't have to represent the 0, because it is already represented in positives. This is assigned to type. I have 7 bits at my disposal, for example, in this case that I'm using a char, and this is the value that I can stock inside this number. Easy. Now, if I say unsigned, what does it mean? Well, it means that I don't need anymore the first bit to discipline the sign of the number, because it is always positive. I'm using this byte only for positive. What does it mean? Well, it means that this time I have 8 bits, namely 2 to the 8. This time is gonna give me 256, which is exactly 128 per 2, of course. It is a power of 2 in this case, right? So every time I add another digit in a binary system, a binary digit, I have the multiplication of 2 of the possible combinations that I can have. For example, here, if I add another binary digit, I could have 512 possible combination, 1024, and so forth. Okay, so in my unsigned char, I have 8 bits that I can use to stock my value, right? I can stock numbers that range from 0 to 255. That's all there is about signed and unsigned. Every time I do unsigned, I get double the space. You understand this point? Pay attention. Because I stop to use the first bit, the most significant bit, as a signed bit. And I use it for the actual value. So I double the possible combination that I can perform, right? Let's see a practical case. Here I have a variable, which is an integer that I called n, is the name of the variable. The value of this integer is 2,147,48,36,47, which is the maximum value representable for 4 bytes. What is this value? Well, it is 2 power 31 minus 1. Why? 2 power 31 because we have 31 bits, we have 31 binary digits, minus 1 because we have to represent the 0, right? The positive. So we get this number. When we say integer without explicitly telling unsigned, by default, it is always signed. So we don't have explicitly to specify, oh, this is assigned. This is going to be automatically performed. Now, what happens if I decide to make this number unsigned? Check it out. As you can see, this time I've declared unsigned int n. And the number that I can represent is exactly the double of before, 4 billion and something. The double because I explained to you that every time I add a binary digit to my number, I double the possibilities. Like, for example, in a base 10 system, every time I add a digit, let's pretend I have the number 10, add 1 digit, now I can represent 10 times more values, right? I get another digit, again, I can represent 10 times more, namely 100 times more than the first case, right? Every time you have an increase of 10 times is exponential. I think it's fairly easy, right? If you think about decimal numbers, if you get $1,000 per month, you get another digit, you can get $99,000 per month, right? Which is fairly a lot to 1,000. The steep of increase is much larger given the base. In a binary system, every time we double the value, every time we get a per true, which is not bad. Essentially, when we have 8 bytes, we have a very large number that we can represent. This is exponential stuff. All right, I think you understand the points. When we say unsigned, we are saying, hey, I don't care about the negative numbers. That's all there is, my friend. Fairly easy. So now you know pretty well that you can write numbers inside your RAM, and for you, it's just a notepad in which you stock values. So let's create a variable together in C. When I create a variable, I'm just telling the compiler something in a very specific way. Like in this case, I have int nb is equal to 42. I want an integer, so I want 4 bytes, and these 4 bytes will encode a value which is in the integer form. So it is not in the float encoding way, in which we have an exponent and we have a different approach. You already know this stuff. So give me these 4 bytes in memory. These bytes have to be signed, namely I need also negative numbers, because here I don't specify unsigned. So the compiler understands that I want a signed data type. Call these bytes nb. This is the name tag that I'm gonna give to this space in memory. This is for me, human. And then I say assign the value 42 to this variable, namely turn on and off the various transistors starting from the least significant bytes, such that this binary electrical state represents the value 42. Easy peasy, which is 101010, right? That's all there is. So you see the power that C gives you when it comes to manipulate the RAM. You can very surgically control the bits. I gave the name NB to my variable. Why? As you can see from the book, you have variable names, little paragraph. Indeed, it is a superb idea to give your variables a very mnemonic, easy to read, short name tag, right? Your code has to be readable from everyone, because eventually you will push your code to GitHub, namely you will share your code with other people. This is very important. So you have to try to write code that is like text, right? It's gonna be super simple to understand what you're trying to do. In this case, it's a stupid example, but I used NB. It's pretty obvious that it is a number. Here I could have used everything for this name. This is not mandatory to use very comprehensible name. This is just good practice. And as you can see from this later paragraph, you should strive for very easy, digestible, readable code, because eventually you will have to read the code you've wrote yourself. So it's very useful to have good mnemonics, because you won't understand even your code a day later you wrote it, because you won't remember the names you gave to your variables, why you gave these names. So you need to put mnemonics everywhere. They will be like little tinders that will spark your memory, and you will understand yourself, your code. So it is for you and for others. As you can see, you cannot use keywords to give name to the variables. This is obvious, because otherwise you will confuse, you will inflate what is a keyword and what is the name of a variable. Now, what is a compiler? As you can see, they're a compiler once, but what is a compiler? Well, my friend, as I told you, computers cannot understand natural languages till now, right? You cannot speak to your computer, hey, just give me the result of this calculation, or create me a Facebook-like software, until artificial intelligence is not becoming a real thing. So we need code, we need functions. For example, here I have little functions that is trying to print in the standard output in the terminal the value 42 plus 1037, but still it doesn't work. I told you in the functions video that this is the way by which we speak to computers. Well, another little lie, because this is still stuff for humans. The real deal is when we compile the source code, namely the code you just saw, the printf with the number. So we have to do this very strange command, which is gcc main, and then we can launch the program which has been compiled. But the real thing is compile the code and then run. We have to translate our code into a binary form that our computer can digest. So the compiler is a translator. It takes source code and transform it to machine code. Now, I wanted to make a video about compilers, but I found online this amazing one from this channel, which is how do computers read code. This is dramatically well done, so there is no point in making a new video from scratch. I prompt you to watch this video if you want to understand how compilers work. They're just programs that translate a source code into binary code. Here you have all the deal. Perfect. Now, as you can see from the book, we have an exercise to do. The first exercise of the book, I think this is magnificent, because you get the progressive overload, you understand the concept and immediately apply into code. This is the way to do. We're gonna do it together. We have to write a program to determine the ranges of char, short, int, and long, both signed and unsigned. We have to include these headers, which is limits.h. My friend, it's time to code. And when we have to code, we have to open our terminal, right? So command space, iterm, boom. And I'm gonna open my terminal. I make a big screen. Now I find myself in the utente space, which is the user space. I changed to the desktop, okay? Cool. Now I need my editor, which is Vim, called Vim, and I call my program limits.c. Okay, and all right, I have my black screen. So we start our little program. Like all the programs, we have to start from the main function. So I'm gonna press I, and I'm gonna insert my main function. I have int, which is the return type of function. Then I write main, which is the name of the function. Open, close brace. Go on the next line, curly brace, closing curly brace. All right, here is the blueprint from my main function. Now inside my main function, I have to write stuff. I have to write my code. Which kind of code? Well, the book is telling me the standard headers, limits.h and float.h contain symbolic constants for all these sizes, along with other properties of the machine and compiler. Let's watch. What is this limits.h? So let's go on Google. Limits.h. Okay, as you can see, in tutorials point, C library. This is another file that contains something. The limit setter determines various properties of the various variable types. The macros defined in this header limits the values of various variables types like char, int, and long. So these are macros. You will know much better about macros in the following video, which is about constants. Now you just understand the overall idea. As you can see, I have char bit, just the value 8. Find the number of bits in a byte. Okay. Char min minus 128. Find the minimum value for a signed char. You see the pattern here. I have signed char max. This is the maximum value of a signed char. You already saw this idea essentially here when I was talking to you about signed or unsigned char. When the number is signed, I have 7 bits available. Namely, I can have ranges from 0 to 127 and from minus 128 to minus 1. That's exactly what you're reading here, right? You have the char minimum that can have this value and the char max that can have this value when the char is signed. But when this char is unsigned, value can be 255. Essentially what I was telling you. In this case, when you have all the bits that can be turned on, you have this value that can be reached for 1 byte. Okay, so this file, long story short, contains all the limits, the data type that can be stored inside my RAM. As you can see, the long min and long max are very, very big numbers because we have 8 bytes at this position. This is a very, very big number, even though it's not often sufficient if you want to make big calculation. Here, as you can see, this site is giving me the ready program. Basically, we can copy it. I was writing it by myself, but this is already done. And just copy it and launch. Okay, so we work by ourselves. So what do we do here? You know all the shortcuts from my video on Vim, right? You do GG to go to the top, and then you do DG, delete ground. Then you do Command V, and you pass all your beautiful copied code. Okay, here it comes. Here you have a full-fledged program. Now we just have to eliminate this. You remember how to eliminate some online. You just do DD, DD, DD. All right. That's the program. You have your main function here, and inside the main function you have your actual code. You have all these printf that you know from the Hello World program. You have this string. We will learn very well about strings when we are going to talk about pointers, which is a beast of data type. It's amazing. I love it because it's very cryptic and hard to use, and everyone hates it because it's too difficult to manage. Like all the things, the more complex, the more power you have. Here you have a conversion specifier, namely this is, please write this string, write this line with a number here, which is this one, the first variable. %d stands for give me a digit in this position. And this is just a new line character. You will know these characters when we are going to talk about the ASCII code. But basically, you have a bunch of printfs that are going to print in the terminal this value, this value, this value, this value. Okay, as you can see here, we have int min, int max, written in uppercase because these are constants. I repeat to you, I will talk profoundly about these constants in the next video. Here we have char min, char max. So basically, these constants come from this file, okay, that contains all these macros. Basically, macros and constants are the same idea. You will learn. Okay, as you can see, you have all these values. Let's try to launch this program. So we have to write :v::quit. Okay. And then what do? We have to compile the code. We do gcc, the compiler. Maybe now you understand what I'm doing. Limits.c. Boom. I pressed enter. Now the program has compiled. And now I should have an output file, which is always a.out. That stands for assembler.out. The name is not important, but this is an executable. This is something that my computer can understand. And to launch this program, I need to write in this fashion: point / and the name of the program itself. Let's try to launch it. Enter. As you can see, this is the output of my program, and I have my string, so before in the program, and basically I have at the output all the constants which are inside the file limits.h. As you can see, an integer has this value, 2 billion and something. You saw here in the slide an unsigned char, the value that can have, which is the double of that 2 billion. This is assigned. We have all these bytes turned on, but the first one, which is a sign bit. So basically, this is the idea behind the size of a data type. We have a certain number of bytes available. Inside these bytes, I can stock up to a certain value. In this case, for an integer sign, the value is this one, 2,147, 48, 36, 47. All right, now I want to show you something. See, I have this file limits.h. This is a preprocessor directive. What does it mean? Well, basically, when we have a program, we want to include something that comes from other files which are in your system. For example, we have the file stdio.h that contains functions such as the printf function that we need to print in the terminal, to print in the black screen these characters, as you saw before, right? We have these characters, and then we have the number that comes from this specific constant, which is inside limits.h. So this file have to be at the top of my program. Hence, we call them header files. These files, as I told you, contain something. They can be functions, that can be constants, basically stuff that I need in my specific program. Let's understand better this idea. I can watch what is inside these files in this fashion. I make the command gcc h limits.c. This is a command that is gonna tell me which are the headers included in my file and specific path of these files inside my system. Let's try to launch this. As you can see, we have a lot of stuff. And we start from here, the first one. This is the standard input-output header. Now let's do something more programming-like. Now you're going to see just a workflow of a quote-unquote programmer. I'm not full-fledged software engineer here. So now I copy this path. The path is just the place in your computer, which this specific file is. And I do cat. It stands for concatenate. Show me what is inside this file and copy. And paste, sorry. Enter. As you can see, I have my big standard input-output file, but I want to find a specific line. So what do? I can do cat and paste. So please show me the content of this file standard input-output, which is this specific path. And then what do? Don't show me that. Pipe the output of this command into another command, which is less. These are ideas that come from my video on the command line. I prompt you to watch. All right, enter. As you can see, I enter inside a specific way of searching inside the file. Now I can search very easily some specific words. For example, I press /printf, enter. Now I have all the matching patterns of printf that I can search for. Pressing N. N stands for new, giving a new match. Like for example, N, and you see that you go down. At the head of the file, I have the next match of printf. Now let's search for the function printf. Namely, let's search for the printf prototype function. And here it comes. You see at the top, I have int printf and something real strange. We're gonna copy this. This, my friend, is the prototype of the printf. This is something that you will understand later. But basically, this piece of code is what I need from the standard input-output file to use the printf function. So I'm gonna copy this. I go back here, and then what do? I go inside my program. I delete the first line, include standard input-output, dd, and then I just do something. Big O to go upstairs and change into the insert mode and pass this specific prototype. Okay, and of course, semicolon. Cool. Basically, what I've done, I've gone inside the file standard input-output inside my system. I took the printf function that I'm using, as you can see, inside my program, and I've copied inside my file. This is not the implementation of the printf function. This is just a prototype, but this is what I need, nothing more. I will explain much better this prototype deal, how do you compile code and everything when we are more on with the course. I want now just to show you that these files contain specific code that I need in my program. All there is. Now let's search for the limits.h file. So let's go back again. So I can do write quit, enter, and then let's launch again gcc header limits. Okay, you can see I have many files. But the thing is that when you include a file, what is going to happen? The computer is going to search for this specific limits.h file in your system in a specific place. Usually is user include. User is a directory and include is another directory. Once this file is found, it's going to include, basically is going to copy paste content of the file inside your program. So your program is going to become really long because it contains a lot of files. So what happens is that inside your header file, there are other inclusions. So you include a file, that file, you have an inclusion for another file, for another file, for another file. You have this recursion. This is how we call that, recursion. It is like a Russian doll, right? You include a file, inside that file you have another inclusion, inside that file you have another inclusion, and so forth. It's like a big Russian doll until you reach all the files that you are going to include in your program. So the file that I want to check now is this one. I recall from sheer practice that is the one with 386. I copy here, and then in the other tab I just do cat, this file, boom. You see here, I have a lot of defines, a lot of things. Now I'm just gonna copy all this stuff, all these defines, all right, till here. And then I'm just gonna go into my program, limits.c. Again, I'm gonna delete my header file, dd, open, and then I'm gonna paste all these defines, you see? Now, let's try this time without any header file to use this program. I'm gonna write. Here there is a little mistake because I cannot have this code here, but I'm gonna write. Here I have another mistake, which is charbit. Why is that? Yeah, because charbit, here it comes, is here. So I need also this piece of code to work properly here. I'm gonna paste here. All right, write. Okay, now everything seems to be pretty fine. Write and quit, gcc, my limits. And now with this flag, with this O flag, I can give a name to the executable. For example, my program ready to rumble, right? It's very stupid, long, uncozy name. So now I do point / my program ready to rumble, enter. And as you can see, the program still works before, because I took inside the other files, which are in my system, the code that I needed, right? You see, that's it. Every time you include another file, you're just taking a file, which is in your system again, and copy pasting inside your program. You saw it manually. This is not the way to do it, just to show what is really going on underneath the hood. So here I took my printf, you see, that I'm using at this level. And here I have all these defines. These are symbolic constant. What does it mean? Well, it means that every time in my program I find, for example, these u char max, unsigned char max, I'm gonna replace this symbolic constant with the value 255. Let's watch inside the code. Here I have char bit, for example. My printf is gonna be called here. I can call it because I have the prototype, so my program knows how to deal with it. And I have the number of bits in a byte. This is a string. This is a specifier because I have this % sign. I already explained this concept in my video. And here I have the D, that stands for digit. So char bit is a digit, and here I have the value, which is 8. Okay? So when the program is gonna be launched, this char bit is gonna be replaced with an 8. So my printf knows this is an 8. Okay? This is what happens basically. So long story short, inside your limits.h that we saw, right? It is the file that is gonna be included. You have a bunch of stuff. These are constant that are gonna be used by your program. Okay, I made a copy paste manually just to show you very practically what was going on. And that's it. It's just telling you what is the maximum value of a specific data type. Now we should do the exercise with manual computation, but we need to use loops, and for now it's case. Maybe we can do in a second moment. The last thing I want to show you, what is the sizeof operator. Very fast. Let's exploit the power of Vim. I do delete ground, and I go back ZZ. Then I do my command boiler, and I do this. I say the size of an int is %d bytes \n. Go to the new line, and here I use the sizeof operator. Sizeof int. Okay, I copy this line yy, and then I passed p. All right. Here I put sizeof char long, and I guess that's it. The size of char, the size of long. Okay, let's save. Why I have a problem? Oh yeah, because it's not giving back a normal digit. It's giving me back a size t, which you will learn what it is, don't worry. It is just a specific digit that the size u is giving me back. So I have to write this zoo, and yeah, now it should work. So let's press ZZ. ZZ is the fast way to go out program. So I'm gonna save and exit. ZZ, of course, upper. Then we do GCC limits, open my program ready to rumble. I made a stupid mistake. I have to do GCC main, not limits. So we can do that. GCC main and out.out. The size of an int is 4 bytes. The size of a char is 1 byte. The size of a long is 8 bytes. As you can see, the sizeof operator is a very important tool that is fairly useful. It's gonna tell you how big is a specific data type in your specific system. So we largely are gonna use this marvelous tool. The last thing from the first lines of the C programming language is this main. When you declare a variable, it doesn't make any sense to give very stupid long names. For example, this is a number, right? Semicolon. This is too long, cumbersome, and overall it's bad practice. You always need to give some very mnemonic, concise, straight to the point names. For example, number. That's perfect. Other conventions that are gonna be useful for you is the way by which you write the name of the variables. We have the so-called camel case. We can write this is in camel case. As you can see, I have for every new word, I have the uppercase, hence camel case. Or we can use the underscore, which is the one I prefer, which is uses the underscore, right? So this is another convention that usually programmers use, namely to split the words. And of course, you cannot call a variable while, because this is a keyword used by the C programming language. This is a loop, or you cannot call main, or for example, for, this is another loop, or switch. Namely, there is a bunch of keywords that are only for C. So your variable names have to be easy to read, easy to understand, easy to maintain for you when you're gonna debug your code. You need to understand the bullshit that you wrote, so you'd better give you some very sparky, some very easy names. All right, for this initial paragraph, I think that's all. Maybe important. When you want to watch how an exercise is done, you can go to GitHub and search, for example, the C programming language exercises. You can go on GitHub and search for other people that have resolved the same exercise. For example, this is an amazing repository, which is on GitHub. And as you can see, you have all the chapters with all the exercises. For example, chapter 2, exercise 2.1, the one we just did. And this dude has made all this very beautiful exercise. So what do we do in this case? We copy the code like this. We go on our Vim, GG, the delete ground, past, all this stuff, ZZ, and then we just run this code. Look how marvelous it is, how fast, how marvelous. Of course, you have to understand the code itself. That's the main point. But as you can see, this fellow has made all the work. He has the code that computes manually the various size of the symbol. So this is a very powerful way to understand what is going on, even only by yourself, basically. And then, when there is something you don't understand, we have our marvelous friend ChatGPT, which is a senior software engineer, which is always with you. Okay. And you ask him all the questions. All right, this is it for this first video of the C programming language. Enjoy, my friend.